Hi friends, today we discuss about the solution of homogeneous PDE involving derivatives with respect to one independent variable only. Here we have the procedure, that is, suppose the dependent variable has differentiated partially with respect to one independent variable, that is x only, then the PDE can be treated as ordinary differential equation, that is ODE. And already we know how to solve the ODE, that is we are familiar with the solving ODE. The arbitrary constants in the solution are replaced by arbitrary function of the other variable, you can say y, giving the solution of PD. Consider example. Solve dou 2z by dou x square plus z equal to 0, given that when x equal to 0, z equal to e to the power y and dou z by dou x equal to 1. Here, using these conditions, we can find the arbitrary functions. Solution. Here, z is a function of x only, that is differentiated with respect to x only. Therefore, given PDE treated as ODE, that is d2z by dx square plus z equal to 0, which implies we can consider an operator way, that is d square plus 1 z equal to 0, where d is differential operator, that is d by dx. This is homogeneous differential equation. We can solve this only the complementary function, that is, before that we consider auxiliary equation. Auxiliary equation is replace d by m, therefore m square plus 1 equal to 0. Take the roots of this, m square equal to minus 1, which implies m equal to plus or minus I. We have two roots, therefore the solution complementary function z equal to c1 cos x plus c2 sin x. But the solution of PDE replaced by the constant c1 and c2, therefore solution of PDE is replacing the c1 and c2 by functions of y, that is z equal to f of y cos x plus g of y sin x. Equation number 1 is solution. But they are given the conditions, therefore we need to find f of y and g of y arbitrary functions. Using first condition using when x equal to 0, the z value is e to the power y. Therefore, equation 1 becomes z value is e to the power y. Keep f of y as it is. Cos 0 because x is 0, and g of y sin 0. But our sin 0 value is 0, therefore the second term is 0. Cos 0 is 1, therefore f of y equal to e to the power y, because sin 0 equal to 0, cos 0 equal to 1. F of y is e to the power y. To find the second condition, second constant, we need to differentiate equation 1 partially with respect to x, because we have dou z by dou x, that is we want dou z by. Therefore, differentiate equation 1 partially with respect to x, that is dou z by dou x equal to, we are treating y as a constant, therefore keep f of y as it is. The cos x is minus sin x plus g of y as it is. Sin x is cos x. Next, using the condition using second condition, that is when x equal to 0, our dou z by dou x is 1, therefore LHS is 1 minus f of y sin 0 plus g of y cos 0. Sin 0 value, that is 0, 1 equal to zero, cos 0, g of, because therefore g of y equal to 1. Therefore, substitute f of y and g of y in a solution, that is equation number 1. Equation number 1 becomes z equal to f of y, that is e to the power y cos x plus g of y is 1, therefore sin x is required solution. Consider one more example. Solve dou 2z by dou y square equal to z, given that when y equal to 0, z is e to the power x and dou z by dou y is e to the power minus x. It is as it is the last example, but the independent variable is changed, that is here with respect to y. Solution. Here z is a function of only one independent variable, say y. Therefore, given PDE is treated as OD. Therefore, d2z by dy square, send this LHS value to LHS minus z equal to 0, which implies d square minus 1 z equal to 0, where capital D is differential operator with respect to y. Now, to solve this equation, first we consider auxiliary equation. Auxiliary equation m square minus 1 equal to 0, which implies m equal to plus or minus 1. Therefore, complementary function z equal to c1 e to the power y plus c2 e to the power minus y. Now, the solution of PDE is replacing the C1 and C2 by functions of x. Therefore, z equal to f of x e to the power y plus g of x e to the power minus y. Call this equation number 1. Now we need to find f of x and g of x using the given condition. Using first condition, that is when y equal to 0, our z value is e to the power x. Therefore, z is e to the power x. Keep above x it is, put e to y value e to the power 0 plus g of x is e to the power minus 0, which implies e to the power 0 value is 1, e to the power minus 0 value is also 1. Therefore, f of x plus g of x equal to e to the power x. Call this equation number 2. Now, to use the other condition, we need to differentiate equation 1 partially with respect to y. Therefore, differentiate equation 1 partially with respect to y. Therefore, dou z by dou y, function of x as it is, e to the power y is e to the power y plus g of x e to the power minus y is minus e to the power minus y. Now we need to apply the second condition, that is when y equal to 0, dou z by dou y is e to the power minus x. Therefore, dou z by dou y is e to the power minus x equal to f of x as it is, e to the power 0 plus minus minus g of x as it is, e to the power minus 0. E to the power 0 is 1, e to the power minus 0 is 1. Therefore, f of x minus g of x equal to e to the power minus x. Call equation number 3. Adding and subtracting equation 2 and 3. If we add we get f of x plus f of x, g of x plus or minus g of x, it cancels. Therefore 2f of x equal to e to the power x minus plus e to the power minus x, which implies f of x equal to e to the power x minus e to plus e to the power minus x divided by 2, which is cos hyperbolic x. Similarly, by subtracting f of x minus f of x, it cancels. G of x minus of minus plus g of x, will get 2 times g of x e to the power x minus e to the power minus x. Therefore g of x equal to e to the power x minus e to the power minus x divided by 2, which implies this should be sin hyperbolic x. Therefore we have f of x and g of x. Substitute these f of x and g of x in the equation number 1, we will get the required solution. Therefore z equal to f of x, that is cos hyperbolic x e to the power y, g of x is sin hyperbolic x e to the power minus y, is required solution. Now we consider one more example. Solve dou 2z by dou x square equal to a square z, given that when x equal to 0, z equal to 0, and dou z by dou x equal to a sin y, dou z by dou x equal to a sin y. Here z is a function of x only. Here z is a function of x only. Therefore given PDE can be written as OD, that is d2z by dx square, transferring the s term to LHS e square z equal to 0, which implies d square minus a square z equal to 0, where d is a differential operator, that is d by dx. To solve this equation, first we consider auxiliary equation replacing d by m. Therefore m square minus a square equal to 0, which implies m equal to plus or minus a. Therefore the solution is z equal to c1 e to the power, it is in terms of x, therefore e to the power ay plus c2 second root minus, that is minus ax, it is in terms of x, e to the power ax to the power minus x. Now we need to find the solution of PDE. Therefore solution of PDE is replacing the C1 and C2 by functions of y. functions of I. Therefore, z equal to f of I e to the power ax plus g of I e to the power minus x. Call this equation number 1. To find f of I and g of I using the given condition. Therefore, using first condition, that is when x equal to 0, z equal to 0. Question 1, that is z value is 0, therefore f of I e to the power a into 0 plus g of I e to the power minus a into 0, e to the power 0, e to the power 0 is 1, therefore f of I plus g of I equal to 0. Now, to use the second condition, we need to differentiate equation number 1 partially with respect to x. Therefore, differentiate equation 1 partially with respect to x, we get dou z by dou x equal to, keep the function of y as it is, f of I e to the power ax, that is differentiation, therefore a is multiplied, the coefficient of x is multiplied, therefore e to the power x into a plus second function as it is, e to the power minus ax, coefficient of a is minus 1. Therefore, dou z by dou x equal to, in both the case a is common, otherwise both the case a is common, we will take a outside, we will get f of I e to the power ax minus g of I e to the power minus x. Using second condition, that is when x equal to 0, dou z by dou x equal to a sin y. Therefore, dou z by dou x is a sin y. LHS a, keep the function as it is, f of y, x is 0, e to the power a into 0 minus g of y e to the power 0, 1. This is 1, this value is 1, therefore a it cancel, therefore f of y minus g of y equal to f of y minus g of y equal to sin y. We call this equation f of y plus g of y equal to 2, and this is equation 3. By solving 2 and 3, that is adding 2 and 3, g of y get cancelled. 2 times f of y equal to sin y, which is equal to f of y is sin y by 2. Subtracting 2 and 3, that is g of f of y get cancelled, we will get g of y, that is 2 times g of y equal to 0 minus sin y, we will get, therefore g of y equal to minus sin y by 2. Therefore, substituting these f of y and g of y in the equation number 1, we will get z equal to sin y by 2 e to the power ax, g of y is minus sin y by 2 e to the power minus x. Therefore, I will take sin y by 2 as a constant, common. Therefore e to the power ax minus e to the power minus x, which implies sin y e to the power ax minus e to the power minus x divided by 2. Therefore this term is sin hyperbolic x z equal to sin y. Sin hyperbolic x is required solution.